Okay, so we're going to spend several days on vectors. We're starting out with vectors today, really focusing on the geometric representation. In other words, with how they look when we, draw them and how we put them together, those kinds of, basic things. Then we'll look at the algebraic representation next time. So let's just focus on concepts, vocabulary words. So a vector actually consists of two different characteristics. It consists of a size or a magnitude. Those words, when we're talking about vectors, we can use those interchangeably. So size or length is another way to think about it. Size, length, magnitude. That's one characteristic of a vector that we have to kind of understand. The second characteristic of a vector is its direction. So its direction. So in context, it would be like velocity, acceleration, force, and displacement. Those have some specific information about direction that are important in those, in those applications. But so the vector has a length and a direction. Vectors that are equivalent or the same would have to have the same magnitude or length and the same direction. That seems kind of just obvious that if they're going to be equivalent, they're going to have to be exactly the same size and pointing exactly the same way. But that's a definition for us. A unit vector. So unit vectors are going to be important to us. We're going to learn how to create a unit vector. What is a unit vector? A unit vector is a vector whose magnitude is 1. So what I would like for you to think about just for a moment, we've used something called the unit circle. We've used the unit circle quite a bit up to now. Does anyone remember why is it called the unit circle? Why is it called the unit circle? What's the deal? Do we remember? That's okay if we don't. I'm thinking that's a no. Okay, it's because the radius is 1. It's 1 unit. The radius of the unit circle is 1. That's why it's called the unit circle. And a unit vector is a vector whose length or magnitude is 1. That's what we're talking about when we use the word unit. 1 unit. Okay, so that's those vocabulary words. That's just a general what those words mean. Let's look at some specifics of vectors. When we look at this vector drawn right here, it kind of perhaps it reminds you, I don't know, if you think back to your geometry days, maybe it reminds you of a ray. Do you all remember what rays look like in geometry? It kind of looks like a ray, but it is not. A ray, with that arrow on a ray, just kind of points in the direction it's going to go forever, right? Forever and ever. Vectors are not like that. They are specifically that long. They don't get longer than that. The arrow doesn't have to do with it continuing. The arrow actually has to do with where it's headed, what its direction is. So that's kind of an important distinction between vectors and rays, is that they are different. I mean, they may look the same, but they are quite different. So if we're going to be sketching a vector, and this is vocabulary words, the initial point or the beginning point is called the tail or the foot. So this little point right here, if we were, using vector language, it would be called the tail or the foot. The terminal point, which is where it ends, I mean, it truly ends. It doesn't keep going in the direction of the arrow. It actually ends. Is called the head. So this little spot right here is called the head. And the arrow is simply showing direction. It's not showing like, oh, you keep going this way. No, it's showing which direction is this vector headed in. Okay, so the length of the vector, the other vocabulary word for us is magnitude. That is length. Length is the same as magnitude. And we like to use these double bars right there. Now, some textbooks use a single one. That's okay. That means magnitude. So if they're putting that there, if they say it looks like absolute value or the double bars, they're talking about the length of the vector. When we write vectors on the paper, notice how, let's look at this one in particular. This is a bolded V, right? It's bolded. That means vector. But when we're writing in our work, we really can't like bold. That's usually if we were typing it or something. So if we're writing it in our work, what we would typically do is we would put a vector symbol over it. And I like to use the half arrow, really, to be honest, because it's faster. You can put a full arrow over it if you want to, but I like to use like the half arrow, and that designates that means this is a vector. So that's how you would write your vector if you're printing it, writing it by hand. Okay, so I'm going to pause here for a second. We're just collecting vocabulary words. It's all we're doing so far. Any questions on the vocabulary words? Okay. So now let's look at the things that we can do, the operations that we can do with vectors. So we can add vectors together. And let me put a little note here. When we're adding them, okay, so when adding or subtracting, the vectors must be placed head to tail. Let me explain what that means. So if I am looking at this vector, we'll call this vector A, and I'm adding vector B to it, they would have to be oriented like this. The ending of vector A would have to be the beginning of vector B. That's what it means by head to tail. Those vectors we can add. Okay, we cannot add tail to tail vectors. So can not add in this form. We can't add them like that. They have to be head to tail. So that's an important distinction for us as we're working through the geometric representation of vectors, knowing the way that they have to be written down on paper or formed so that we can add them. Now, we certainly could fix this one over here, so we could add it. We could fix that by moving. We're allowed to move vectors around. So I could actually, okay, I'm going to try to copy it. I don't know if it will work. Okay, so if I take this vector and I grab this part, this bottom one, and I move it up, then I can add them together. So I can move them. I can move the vector as long as I don't change its length or direction. I can move it around anywhere I want to. So I could rewrite the vector so that I can add. So we can add these. Okay, does anybody have any questions about that? Yes?
How does that not change the direction?
So the direction is simply like, if we want to look, let's just focus on this piece of this vector right here. I'm going to try to, so let's focus on this one. Okay, what the direction means is as we are thinking about this angle measure, that's like the direction is actually an angle measure, is that angle measure the same as this angle measure? And it is. So it has the same direction. The direction has to do with an angle measure. Okay? But it can be slid anywhere on the page. It doesn't have to be lined up with the origin, although I would recommend you lining it up with the origin. It makes our life easier. Okay, any other questions? Okay, so let's look at what happens when we add two vectors together. So we've got, here's vector AB, and we are moving vector BC so that they line up properly, so they're head to tail. So we just took vector BC and we slid it down and connected it. The resultant vector is the vector that connects the original beginning to the end. That's called the resultant vector. It's usually done in like dotted lines. Do you have to? No, but that's what's usually done. Okay, so that's the resultant vector. Okay, and that's what this means. This is doing it algebraically, what I'm circling right now, which we're going to work on next time. We're going to work on algebraic next time. Today we're just working on drawing them and adding them and such. If we subtract vectors, we can also subtract them, and I want to focus on this little thing right here. So what does that mean? That means that, okay. This means that the director has it's the same length, but it goes exactly in the opposite direction. So if I were going to do like the opposite of BC, then I would draw it exactly the same length. Okay, you're gonna have to, approximating, but the arrow would be on the other end. That would be the opposite of BC. And that's the opposite of V. It's just basically I guess you could think about it like 180 degrees rotated. Or just take the arrow off one end and stick it on the other. That's basically virtually what we're doing. So we have already talked about this note that vectors can be moved, but they have to keep the same magnitude and direction. So it's like if you put your hand on, I don't know, a pencil, and you just move it left or right or up or down and don't change, the pencil doesn't change its length, right? It's going to be the same length anyway, and you don't allow it to rotate at all. That's like moving a vector. You can just slide it around anywhere you want to. Also, so a scalar, this is another vocabulary word. A scalar is a real number. You can multiply a vector by a real number. You could double the length of the vector if you wanted to. So up here, if I wanted to do 2 times vector AB, what it would mean is I would basically draw it twice the length. And of course I have to measure it, but that would be 2 times vector AB. You just take the length and you double it. And that's okay. That's called multiplying by a scalar, and you can certainly do that. The 0 vector represents no displacement. We don't really do much with a 0 vector, but they're just calling it out as like a vocabulary word. It's a bold 0 or a 0 with a half arrow over it. And those are our vocabulary words for this section. Are there any questions about any of the concepts or vocabulary words that we're learning? Okay. So we have a couple of examples. The first one, of course. So on your homework, it's in the textbook. I would recommend that have y'all ever like printed your homework out or printed to PDF before? Since you're going to be doing some drawing, I would really recommend that you do that. You can print the homework assignment to PDF and then just put it in a OneNote document, or you can actually physically print it out. I think it would be easier for you to work with if you were actually writing, like moving the vectors by hand. That's just a recommendation. So they want us to sketch the vector indicated. So we're looking at 2u plus v, and we're going to sketch it on the next grid. So let's think about what that means. So u is, if I'm talking about where it starts, it goes left 2 and it goes up 1, 2, 3. Okay, that's what u does. So I'm going to start my 2u from the same place. I don't have to. I'm just trying to make it easy for us. And instead of going left 2, because I'm doubling it, I'm going to go left 4. 1, 2, 3, 4. And instead of going up 3, I'm going to go up 6. So 1, 2, 3, 4, 5, 6. So this is the new end to my 2u. And I'm going to use a ruler just because it just will make it a little bit straighter than me trying to do it by hand. Of course, it's always iffy whether I can get it to do right. Okay, so here's we're going with that. That's fine. Okay, there's my vector. It's going this way. And I'm going to label it. This is 2u, and I'm putting my little half arrow over it. That's what that vector is. I want to add to it v. Now I'm not changing the length or direction of v. It's just going to be exactly like it is. So what does it do? Let's see. V goes right 2 and up 1, 2, 3, 4, 5. So I'm going to start v right here at the end of u, and I'm going to go right 2. I'm going to go up 1, 2, 3, 4, 5. So it actually ends right here. Okay, so there's that vector. Okay, and I'm just going to call that v, because that is just vector v. Okay, is everybody okay so far? So I doubled vector u, because that's what they told me to do, and I'm adding vector v to it. Notice that I have the vectors placed head to tail. That's what we have to do. The resultant vector is the connection of the beginning point to the ending end point. So let's go with our okay, so let's connect this together. That's called our resultant, and it's in this, in that direction. And our resultant vector, the name of our resultant vector is 2u plus v. So we're just labeling our diagram. So that's physically sketching it. How are we doing with physically sketching on a grid? I think the grid paper makes it nice, and I know on your OneNote you can have a page, you can create a page and put grid paper on it. That would be quite handy for you in working with these. That would be a good idea. Do y'all know how to do the grid paper on your OneNote? I bet you do. You probably know better than I do. Okay, so let's look at number 2. So we're going to do a scale drawing showing a force of 20 newtons. Now this is, that N means newtons. Maybe you remember it from physics, maybe you don't, I don't know. So that's a measurement of force, newtons. They're wanting us to make a scale drawing showing a force of 20 newtons pulling an object east and another force of 10 newtons pulling the object in the compass direction 150 degrees. Draw the resultant force vector and then find magnitude and direction. Okay, so let's go back and pull this apart. So this measurement right here, this is the length or magnitude of the vector. I mean, that's what it is, it's the length. And I'm going east, and hopefully we know east would be like going right. So I'm going to go ahead and draw my vector. And we'll just do, I don't know, probably can help me with the size of it also. That's a great idea. So it's hard to tell. So we'll make it like that. That's fine. A little bit bigger. Okay. So this is 20 newtons and it's pointing right because we're going east. Okay, so that's my first vector. They're wanting us to, let's focus on this word right here, this resultant. This word means, it means add the vectors. That's what the word resultant means. Draw the resultant force vector. They're wanting us to add the vectors and draw that dotted line thing. That's what they're wanting us to do. Okay? That's what the resultant. So the other thing we need to focus on is this whole compass direction. So I'm going to go out here to the side and we're going to do compass direction. I just want to talk about compass direction of 150 degrees. What does that mean? A compass direction is different than just a regular direction. Normally in Precal, we start our angle at the x-axis and we rotate like that. That's how we measure in Precal, right? If we're not in context. But if we're in compass direction measures from the north line. Compass direction measures from north. So if they say compass direction, we're supposed to be measuring from the north. So let's do this is like a line right here. So this is like our north line. And just so that we can get a feel for what we're doing, let's do, like an east-west line, if you will. So if we want to go 150 degrees, and we know we have to measure from the north line, we're going to start our angle measure right here at the north line, and we're going to rotate. Okay, that would give me 90 degrees. 150 would be down here somewhere, right? That's where 150 would be. And our vector would look like this. That would be a compass bearing of 150 degrees. Okay, this is explaining compass direction. Okay, so we measure from the north line, we rotate the 150 degrees, so past 90, not all the way to 180, so 150, and we draw our vector. So with that concept, let's attach that compass direction of 150 degrees, the 10 newtons, let's attach it to our drawing right here. I'm going to draw like a little north line, and we're going to rotate 150 degrees, be about right there. And so now I'm going to draw my vector. It needs to be, I'll try to use the ruler again. Let's see if it behaves. Actually, you could actually get like a 50 degrees. Okay, well, there you go. There's actually 50 degrees. It shows you on the ruler. And I need it to be half the length of that 20 in. So we'll go like, I don't know, about right there. It doesn't have to be perfect, but it wants you to do a scale. A scale drawing means you should try to get the components roughly, you know, you wouldn't want the 10 Newton vector to be 3 times as long as the 20 Newton direct, vector. So this would be our 10 Newtons length, and this angle measure is 150 degrees. Okay, I want to pause here for just a second. Are there any questions about how to do compass direction of 150 degrees or how to draw these head to tail?
I'm confused about the length of 10 newtons.
So if we have a ruler, which I'm going to pull the ruler out, so this length would be like, I wish I could mark on the ruler. You see how it's like an inch and a half, like about an inch and a half? That means that this one has to be like 3 inches, which I may not even have it the right. So 1, 2, no, I have it 2.5 inches. So the 10 newtons is too long. It's a length. Think of it as just like 10 units long.
So it just needs to be like reasonably like half of it.
Exactly.
Okay.
Just reasonably half of the other one, because the other one's 20, that one's 10. It doesn't have to be perfect. You don't have to measure it to be perfect, but it just has to be around that.
Okay. So for the compass direction, you tap from the top like clockwise.
You do, and I know that's totally messed up. My husband and I have arguments about that. I'm like, that's the wrong way to measure. He's like, no, that's the right way to measure, because he's a pilot. He's like, you measure from the north. I'm like, no, you don't. You measure from the x-axis. He's like, what? Anyway, that's a side note. All right, so yes, when we're in compass directions, we have to go into context instead of in regular trig world. Regular Precal world, we measure from the x-axis counterclockwise, but in context, when we're doing compass measurements, we measure from the north line like the y-axis clockwise. That's just kind of a thing we got to remember. Even if we don't like it, we have to remember it. I'm just saying. Okay, so are we okay so far? Everybody okay? All right, so we've got the 2 vectors drawn. Now we want to draw the resultant vector. So let's connect the very beginning to the very end. So here's our resultant. All right, there's our little arrow. So that's our resultant vector. Okay. Great, we have our picture. What they want us to do is find the magnitude and direction, and it's so great being on the computer because I can actually like copy, and because let me just say that when I try to draw all over the picture that I've just created, I usually mess it up. I'm just going to be honest, I usually mess it up. So I would leave the original picture alone, don't mess with it, and recopy it, because I'm going to draw like a triangle. We want to know the magnitude. The magnitude means the length, so we need to know x. That's what we need to know, is x. Okay, well I know that angle is 150, and I know this angle right here is 90 degrees. Is there a way that I could find this angle of this triangle? We're thinking in terms of triangles now, ladies. Is there a way that I can find that triangle? Let's make it a different color so it's more obvious.
Add 90 and 150, subtract it from 360.
Absolutely. We add 90 and 150, subtract from 360. So I take 360 I'm taking out the 90, I'm taking out the 150, and that gives me 120. So this angle measure is 120, let me get rid of that stuff in there. This is 120 degrees. Okay. So we have side angle side, and we need to find that x, that length. What are our ideas thinking about our oblique triangle trig that we worked on just a little bit ago? What might be best for us to find side x? What should we use? Okay, would we use law of sines or law of cosines? When we have more sides than angles. Cosines, we would use law of cosines, exactly. So here we go. Yay, you thought that you could forget that. Nope. All right, x squared equals 20 squared plus 10 squared minus 2 times 20 times 10, cosine of 120 degrees. We put it in our calculator, and I know we've done a lot of work on this, so I'm not going to pull my calculator up, but we put it in our calculator. We get x squared is 700. So x is, we would square both sides. It reduces to 10 root 7. So they wanted to know the magnitude, so we'll just list it over here. So magnitude is 10 root 7 newtons. Okay, great, we got that. Now they want to know direction, and we're in the compass world. Okay, so the direction is going to be in the compass world. So let me show you where our direction is. We want the direction of the green one. The green vector is what we're focusing on. And we go to the beginning of the green vector. And we're doing our compass stuff. We rotate till we get to the vector. That's the angle measure we need. This is the direction. Now, if we weren't in context, we would do x-axis business. But we are, so we have to go from the north line, start the north line, and rotate clockwise till we hit our path, our vector. Since that's an east line, I know that this part right here is 90 degrees. Does everybody agree with that? Is everybody okay? That's 90 degrees. I need to find, and I don't know, we can call this, we'll just call it A. I need to find this angle, angle A, that little bitty angle in the triangle. Ideas on how we can find angle A out of our triangle. Which rule should we use? Law of sines, law of cosines. Those are our choices. Sines, law of sines. We should do law of sines. So we do sine of 120 degrees over, what was x? It was 10 root 7 equals sine of A over, what was that, 10? And then we've done this quite a few times. We should be fairly comfortable with it. When you're done, the measure of angle A is going to end up being 19.1066 degrees. So to get my direction, what do I do with that measure from angle A? I add 90 to it. So I do 90 plus 19.1066, and that gives me 109.107. So we're going to say direction is 109.107 degrees. Okay. I want to pause here for a second. How are we doing? Any questions for me?
Why did you add 90 to get the direction?
Because I needed this whole angle right here.
Oh.
The whole thing for my direction. I have to rotate from the north line all the way to my vector.
Okay.
So I had to add that little piece to it. Okay, other questions about that? Before we stop, I need to talk to you about one other thing about direction. There's some problems in your homework that use a little bit of different notation. that we will get to when we work on the algebraic mode. So for example, they could say vector v is, I don't know, let's say 2i minus 2j, which is the same thing as the chevron 2 comma negative 2. Let's talk about how we would draw that. These two mean the same thing. They're written in different forms. Okay, this is my x direction, this is my y direction. Basically, to draw the vector, if you do it in standard form, which you should, is starting at the origin, you just go to x2, y negative 2, and you draw your terminal point, and that's your vector. That's the vector 2, negative 2. So I just needed to kind of show that to you because I do have some questions on it with the vector written in that form. So that would be 2 spaces this way, that's my x, and it would be negative 2 spaces that way, that's my y. And you could make a triangle with it, a right triangle, which I would encourage you to do to answer whatever questions that they're asking you. Okay?